Yeah, so welcome back to the second lecture. Yesterday, we did a little bit of an introduction into graphical models. And today I'll continue. I'll finish off my introduction with a bit of a review and then go more into undirected graphical models today. So again, like yesterday, please just feel free to interrupt me whenever you have questions. Just speak up, or if you feel more comfortable putting it in the chat, feel free to put it in the chat. Good. So let me just start with a brief recap. So I introduced graphical models last time as a way to represent distributions or a distribution using a graph, which helps you in terms of, depends how sparse the graph is, but it may help you in terms of computations, to perform computations, and also for interpretability of the model or whatever you are trying to model. In particular, if you're thinking of the directed setting where the graph might represent causal relationships. And so we had like this little framework here that we kind of wanted to fill in last time, where we have a graph which should represent the distribution. So the graph tells you how the distribution factorizes. But now, of course, also, and then factorization of a particular factorization of the distribution will also imply certain conditional independence relations. But the graph, if you look at it graph theoretically, then missing edges also implies certain separation statements in the graph. And now, if this theory is as nice as we hope it to be, and it is, because it has held for so long, then these separation statements should also be exactly the same as what you get from the factorization out. So these conditional independence statements that you get out of the factorization. And so we would like to see here that there is an equality, that somehow factorization with respect to a graph and separation statements in the graph somehow give rise to the same thing in the end. So that is all nice and intuitive. And so we went through this, how should one define factorization? How should one define separation in the directed setting? We also discussed that there we take DAGs because it was motivated based on, to represent causal relationships, which are always forward in time. So you have, a factorization with respect to a DAG is kind of something that is very, very intuitive, where you just start off at the top of the DAG, right? At the most up parents, I guess. Maybe I just draw it, right? You just start off all the way at the top at any of your root nodes up here. Since it is a DAG, right, there will always be some root nodes. Might not just be one, there might be multiple ones. And then you just write out your factorization in this way, where you have you start off with all the root nodes. These don't have any parents, and then the distribution just factorizes so that every node is a product of. So the distribution is a product of every conditional here, where you have the conditional of a node given its parents. Okay, so a very, very intuitive way of structuring the distribution. So that's what it means to factorize with respect to a DAG. And this implies certain conditional independence relations. And we saw in particular that it implies conditional independence relations where a node is independent of all of its non-descendants given its parents. Okay, so a node here would be independent of this node here, which is a non-descendant given its parents. So given this node here, for example. Okay, that's one example. We also saw that these conditional independence relations that you get of this form here are not all conditional independence relations that you get from factorization. And we briefly discussed, and I won't go too much into detail here. I think you should look it up if you're interested. But there is a way from the graph to read off all conditional independence relations that can actually be implied. This is just like a set of rules that we kind of went through. But which, you really have to have like a couple of hours of just doing some exercises and going through it a couple of times for yourself to really somehow internalize these rules. But I think what is important is that there is a graphical way of reading off all of the conditional independence relations that are implied by the factorization itself. Okay. And so we saw this, that, in the directed setting, we have this very nice thing. So this picture here, in fact, is really holds, right? So factorization is equivalent to the global Markov property, which is again equivalent to the local Markov property. So everything here is really nice. We didn't finish going through the same picture in the undirected setting. We did describe there. So in the directed setting, it's very easy or very intuitive to write down a way of factorizing a distribution with respect to a graph. And then kind of from there, you get out these Markov properties. This is kind of harder to define, right? But you define them in such a way so that in the end, you get equality here. That's really what you want. Now, in the undirected setting, we'll go the other way around. So for an undirected graph, there is a very intuitive way of writing out separation statements. And then we'll want to find a factorization so that in the end, we get something like equality here. Okay. And so we already discussed, right, in the undirected graph, a very then probably most intuitive way of writing out separation statements is just, two sets of nodes are separated given a third set of nodes. If you remove the third set of nodes, there is no connection. There is no paths between this set of nodes and this set of nodes. Okay, so that's graph theoretically the kind of way you would define separation in an undirected graph. And let's just define that as the Markov property. Then obviously you can also have something like, before we had a local property here, we can just easily write down a pairwise property, right? If you just look at two nodes, well, then, and you just, and there is no edge between them. So you have two nodes with no edge between them. Well, then that means that if you remove all other nodes, then certainly they are going to be disconnected, right? So, from the global Markov property, it certainly implies this kind of pairwise Markov property, right? Which is a, like what we had before, we had like two different kinds of Markov properties, right? Where one certainly implies the other. And then interestingly, in the end, we figured out that they're actually equivalent. And so similarly here, I'm just writing out another Markov property, which is certainly weaker than the in terms of just sets, right? In terms of just sets of conditional dependence relations, well, then the pairwise, the independence relations in the pairwise Markov property are certainly contained in the conditional independence relations in the global Markov property, and they are in general not the same. But the question is, as distributions, maybe they're still equivalent, right? Maybe the same is happening as what is happening here. Again, as sets of conditional independent relations, one is strictly, or in general, strictly included in the other one. So usually, set of conditional independence relations, it's strictly like this. But, since we know that these are distributions, one can actually sometimes still show, and in this case, you can show that they're in fact equivalent. And so that's somehow what we would hope that we could also do in the undirected setting. Now, the undirected setting is not as nice, but it is nearly as nice. And I will get to the theorem, to the equivalent theorem that we have for the directed setting where everything is nice and equivalent. I'll get to it on the next slide. But unfortunately, in general, this is not the case. Okay, so this direction here does in general not hold. But there are certain conditions under which it holds, and we will get to it in the next slide. So certainly this here holds, but the other direction does not hold. Well, okay, so now we want to define some way of factorization of the distribution according to an undirected graph so that you get out the global Markov property, right? So that factorization will actually imply the global Markov property. And hopefully even vice versa. And again, you'll see that this is maybe a bit harder, but hopefully, at least in this direction, we'd like to have a factorization that will really give rise to this kind of global Markov property. And, I mentioned last time that, some kind of ways of trying to define it by somehow having factors here that just take into account your neighbors will actually not work. In particular, you can show that if you have well, you'll have to define it in a very special way. So if you just have a cycle like something like, the marginal distributions over just your neighbors will not work. So if I have something like this and, say now like something like what we did for DAGs, right? We took a node and its parents. And so one could think like, well, maybe now it's undirected. So I'll take a node and its neighbors. And I'll just write it as a product over all these marginals, and maybe I add a normalizing constant. So this will actually not give anything that is constant. And you can show this for yourself. But here, what actually does give you a way that is consistent and will imply the global Markov property is using what people in physics have used in statistical physics, namely motivated by the Boltzmann, also known as the Gibbs distribution, which you have here, which I'm sure many of you have seen. So this is the Boltzmann distribution. And you see how they define the factors, right? So they have, so what are the factors in this kind of factorization? Well, so what I'm writing out here, what this is this is the set of all, so by CL of G, I mean the set of all cliques in the graph. Okay, so these are all fully connected subgraphs in the graph. And you see that they have a product over all of the cliques in the graph, right? Because the exponential, the sum can be taken outside. So really it is a product over all of the cliques in the graph. And then if you look at it, so then you'll have an exponential. So the exponential will always give you something non-negative or positive. And so in that case, and here we'll have these potential functions. And again, like really motivated by this physics way of defining the distribution, we'll use that all these potentials are actually non-negative functions. Okay, and that's quite interesting. So that this way of factorization, so there's just a product over all cliques in the graph. Note that these things here don't have to say integrate or sum up to 1, right? They have no other assumptions other than just being non-negative functions. And just this kind of factorization, we'll see, in fact, implies the global Markov property. Okay, so this is the right way of factorizing so that everything becomes nice and consistent, kind of like on the previous picture. And I'll show you the main theorems here. So first of all, this is something that one can quite easily show, namely that, oh, perfect. I'll take the question just afterwards. Namely that factorization implies the global Markov property and implies the local Markov property. And we'll talk about the other direction just after I answer this question. So there's a question about, are all cliques maximal? So without loss of generality, you can assume that all cliques are maximal, right? Because if I have two non-maximal cliques, say I actually have just a triangle. So in this case, you could write it out as a product over all of the cliques, but then I can just define a new potential function, right? That takes into that merges all of the non-maximal cliques and just has one potential function for the maximal clique. So without loss of generality, you can always assume that this is just a product over all maximal cliques. Great question. Okay, so one can show, and really these proofs are not so hard, and I mentioned last time that you will find all of the proofs in Lauritz's book, and I had the reference there. So you can show that, factorization implies a global Markov property and implies a local Markov property if you define factorization as, this product over all of the maximal cliques where the potentials are just non-negative functions, and they can be any non-negative function. Then you'll actually just get out all of these implications. Now, of course, the question is the other way around, right? So this way around. And so here is a theorem that is, one of the most important theorems for graphical models, which says that under some assumptions, namely, in particular, you can show this, that if the distribution is strictly positive, so think of, for example, a Gaussian distribution, then in fact, you can go the other way around as well, okay? Then the local Markov property will imply the global Markov property will imply factorization. Now, Hammersley and Clifford actually never wrote up this proof because they always thought that this condition here was kind of unnatural, and they wanted to try to get rid of it. Besak, in the end, was the person who wrote up this proof. But what turns out in the same year as when Besak wrote out the proof, Mussouris actually showed that, in general, the global Markov property does not imply factorization. So you really need an additional assumption. Now, there are different kinds of additional assumptions, but the most natural one is this one here. So you really need an additional assumption, and one of the natural assumptions that gives you this equivalence is that the density is larger than 0. Okay, so you need to have an additional assumption here, otherwise all of these equivalences are not true. And you can also show that this should be pairwise, but it doesn't matter. Local, there is also a definition of a local Markov property, so it doesn't really matter, it's okay. But I only defined a pairwise Markov property on the previous slide. So in general, you can also show that the pairwise Markov property or the local Markov property does in fact not imply the global Markov property. Okay, so you really need this assumption that the distribution is actually positive, strictly positive. Okay, so that's kind of the full story for undirected graphical models. And today we're really going to concentrate on undirected graphical models, and then tomorrow's lecture will be on directed graphical models. Okay, so today is on learning undirected graphical models. Tomorrow is on learning directed graphical models or directed acyclic graphs. And today I'm mostly going to concentrate on the Gaussian setting. So I have the Hammersley-Clifford theorem, right? Because the Gaussian is in fact strict positive everywhere. And something that I will use a lot, and this would be a really good homework problem for everyone to do, is the following. So assume that you have a distribution that is Gaussian and that it factorizes according to an undirected graph. Okay, so that means you go back here. It factorizes according to an undirected graph. So, in particular, it can only have terms here that, every term has to only depend on variables in a clique. Okay, there cannot be terms that go across different kinds of cliques. And if you just write out the Gaussian density function and, you get, well, then in the sum in the density function, you cannot have certain terms, right? Namely the terms that go across cliques, you'll actually find out, and this would be very good to show, that in fact what you'll get is that whenever you don't have an edge, and this will imply, and it's equivalent to, that in the inverse covariance matrix, you'll have a 0 in that position. Okay, so whenever you don't have an edge in the graph, then in the Gaussian distribution, this factorization means that you need to have a 0 in the inverse covariance matrix. This really just comes from writing out the density function and writing out what it means to factorize according to an undirected graph. Now, we already know, I mean, if you believe this theorem here, then we already know that factorization is equivalent to global is equivalent to pairwise or local. So the pairwise Markov property is of course this, right? So definitely factorization will be equivalent. I mean, if you believe these theorems, it will be equivalent to having that every node is independent of a node is independent of another node when there's no edge between them if you condition on everything else, right? Because if there is no edge, I remove all nodes, then certainly they are separated. But so this is kind of trivial. Well, it follows trivially from these theorems up here. But what would be nice for you to do is actually to not use the theorem and try to show that this is actually true. Okay. So try to show that, from factorization, you just get this equivalence, and then, reason through conditional independence relations, etc. Why does a 0 in the inverse covariance matrix mean that the two nodes xi, xj are independent given everyone else? Okay, I think this would be good. And this is an instance. This, of course, means that the local Markov property holds in the Gaussian setting. Is there a question? No. Okay, sounds good. Okay, good. So, so I hope this will be a good homework problem to do. And we'll be looking quite a lot at the Gaussian setting in this lecture. So now would be good time to ask questions if there are questions. Okay. Okay, so let's get started. So that's the background on undirected graphical models. Okay, so we have Hammersley-Clifford theorem, which tells us that under positivity of the distribution, we actually have the factorization is equivalent to any of the Markov properties that we defined. Okay, so now what we would like to do is actually learn the graph. Okay, so I would like to go from, if I go back here to this little picture. So everything that I'm going to do now and in the next lecture is really about learning the graph. Okay, so I would like to learn this graph here. I'm not given the graph. I would like to learn it. So one way of doing that, if you look at this little picture, is, well, you know, I'm given samples, right, from a distribution. Well, from the samples from the distribution, I can infer conditional independence relations. And then, since conditional independence relations, correspond to, or should correspond to, these separation statements, then if you have this equality here between the two, then from the separation statements, I can then go back to the graph. Okay, and so that's kind of the path that we would like to go. So from conditional dependence relations, we learn separation statements in the graph, and then from separation statements in the graph, we learn the graph itself. And that's what we're very, you know, this clean path is what we're going to use when we're actually going to learn the graph in the directed setting. Okay, so this is one of the standard paths of actually doing it. Other ways, and really they're kind of equivalent to this conditional independence, but how you're setting it up is maybe a bit differently, is to try to learn the graph via an optimization problem. So for example, you know, you can maximize the likelihood function. And the problem with maximizing the likelihood, so that means, right, I'm trying to find the parameters that maximize the probability of seeing the data that we have. Now, for that, if you just, you know, usually, you know, so if you would just take the full, well, you take the full graph, right? And now you're just hoping that some of the edges come out to be 0, and that means that I can remove these edges. So I take the full graph, I do maximum likelihood estimation so that I learn all of the parameter weights on this graph. And then I'm saying like, hey, if they're small enough, I'll just get rid of them. Or you can even do a hypothesis test to get rid of them. Then you're kind of testing again. So that's why they're kind of equivalent, is that you're actually testing about, again, conditional independence relations. It's just that you're setting it up slightly differently. You can also use something like a penalization, like, for example, you do a, you know, a BIC penalization so that you already get a little bit of a sparser graph out, meaning that, you know, you hope that some of these parameters, you want them to be sparse, so you can add, for example, an L1 penalty. So these are two different approaches, but you know, you can kind of show that you can really go between them, but it's just different ways of setting it up. So either I just start with conditional independence relations, I get to the graph, or I set up an optimization problem over the set of parameters. And you know, I want that set of parameters, I want many of them to come out to be 0, because the parameters correspond to the edge weights. And if they come out to be 0, that means that I can remove the edges. Okay, so that I get a sparser graph that will represent the distribution. And so in the undirected setting, what I'm going to do here today is to actually use that approach. Okay, so I'll use the optimization approach for the undirected setting that I'm describing today. And I use the approach coming from conditional independence relations and learning the graph in what I'm discussing tomorrow. Okay, but just note that, you know, there are two approaches. You can see learning a graph as coming from conditional independence relations or writing it out as an optimization problem, and you can really go between them back and forth. And so let me show you how you can actually write this out as an optimization problem. So if you've done this many times, you've probably already seen the Gaussian likelihood, but you just write out from the density function, you can write out what is the probability of seeing the data in terms of the parameters. Okay, so that's what is known as, you know, and then you'll get a parameter estimate for the parameters in your Gaussian. So here, how I'm going to denote these things. So I have a Gaussian distribution with a covariance matrix sigma. And I'll denote by K the inverse covariance matrix. Okay, now what I had on the previous slide is exactly this statement, right? In a Gaussian graphical model, you have an edge if and only if you don't have a 0 in the inverse covariance matrix, if and only if xi and xj are dependent given everyone else. Right? That's exactly what I had written out as a homework problem on the last slide. And I will use as until now, p is the number of variables, and n, now we will also have a sample size, n is the number of samples that we get. And here I'll have my sample covariance matrix. So I just get all my samples and I'll build my sample covariance matrix. And the sample covariance matrix, since this is, my mean is 0, S is all of your samples. So this is now a P times N matrix times X transposed. So this is a N times P matrix. So S is of size P by P. And so, in a Gaussian, since it has, measure everywhere, the rank of this matrix is just going to be the minimum of N and P, right? Because it has measure everywhere, so you won't have any dependencies in here. So here the rank will be the minimum of N and P. And, now some of you have probably maybe not seen the Gaussian likelihood. And so you would have to believe me that, this is the likelihood function when you actually write it out. So to obtain, so we would like to estimate now this sigma or this K here. To obtain the estimates of K, what you do is you just maximize this likelihood function. So this is the logarithm of the determinant of this matrix, which is positive definite, minus the trace of the sample covariance matrix. This is given to you by the samples, and this is the argmax over all K. And this is a positive definite matrix. Okay, so this is the optimization problem that we're solving. And now, of course, zeros in here, right? Zeros in here correspond to a missing edge. So what you want is to, if you want to learn the graph, you actually want to learn this matrix K here, right? So I want to learn this matrix K here. So I want to learn where are there zeros. And, people asked last time, will we also talk about estimating the edge weights? Well, this here would actually give you the edge weights, right? Now, the problem is that, if you have small number of samples, and that's often the case, right? My number of variables can actually grow. I might have very, very large graphs, and the number of samples might be smaller than the number of variables. Then this optimization problem actually goes off to infinity. Okay, so then, this MLE here does not exist. So here you're actually just going to go off to infinity. And if you have many more samples than the number of variables, well, then you'll not get any zeros in this estimator here. Okay, in general, you'll not get any zeros in here. So that means that your graph is always the complete graph. Okay, and that's maybe not what you really want for computational questions, but also for interpretability, right? You don't want to just get out the full graph. Obviously, the full graph can describe any distribution, so that doesn't put any constraints on the distribution itself. So what people do in this setting, and this is the standard thing to do, is I want it to be sparse, hence let me add some penalty to it. And if you add an L1 penalty, for example, then it remains a convex optimization problem, right? Note that this is a convex optimization problem. So I'm maximizing a concave function, right? Log det of a positive definite matrix is concave. And then here I have something that is linear in K. So this is a concave function that I'm trying to maximize. So I could add, something like an L1 term here in the end in order to try to make this matrix that comes out, or the graph that comes out, right? Because the graph corresponds to the non-zero pattern of this estimator here. So I could actually try to make it sparse. Now, this is a standardly used estimator. This is known as graphical lasso. Okay, so this is how, when you assume Gaussianity, how often you would actually learn the underlying graph. So you maximize the likelihood function. Again, this is over K. Okay, so this is an optimization problem over K. S is given by the data. Lambda is a fixed parameter that you need to tune. And depending on how large you choose out lambda, it will become sparser and sparser. Although I will talk a little bit about that. That's actually not quite the case, but in general, right, with increasing lambda, it will become sparser, but it's actually unfortunately not monotone. So it's not the case that, you know, when you increase lambda, that always only edges can disappear. In fact, it's a bit unfortunate that you can increase lambda and sometimes an edge can come back in and another edge goes out and then another edge comes back in and goes out. It's not monotone. So it's really something that is quite annoying in terms of actually tuning lambda. But there are results that, you know, for if you choose your lambda correctly and under very strong assumptions that you cannot check from the data, then in fact you will learn the correct graph even in the high dimensional setting. Okay, so but the problem is really always this choice of lambda, and that you have here some assumptions that, you know, you cannot check from the data. And so, but if you choose your lambda correctly, then you will be guaranteed to learn the correct graph. The question is just how do you choose lambda? And the problem is that, you know, if you just sweep through lambda, you know, some edges can come back in and go back out again, which is a bit unfortunate. And there is another disadvantage if you're a statistician, which is kind of, you know, something that you would, well, that is maybe a bit disturbing from a statistical point of view is here. If you look at the MLE, whether you plug in a sample covariance matrix or a correlation matrix, meaning that, you know, I just normalize the matrix so that I have ones on the diagonal, it actually gives you out the same estimator. Okay, you can easily write it because the diagonal will come out. And so it's just a constant. And so that one doesn't matter. So you'll see that whether you plug in the sample covariance matrix or the sample correlation matrix, you actually always get out the same estimator. Now, the problem when you add in here this, this L1 penalty, that's in fact not the case. Okay, so sometimes if you use, or in general, if, you know, you have to decide here, what are you going to plug in? Are you going to plug in the sample covariance matrix or are you going to plug in the sample correlation matrix? And you might actually get out very different graphs depending on what you do. So that's really quite unfortunate in terms of this estimator here, something that you really don't want to have to deal with. That it also depends on, you know, whether you use the sample covariance matrix or the sample correlation matrix. But this is one of the standard approaches for learning these graphs. And so what I want to do today is somehow, since this, you know, lecture here is all about geometric constraints, to discuss one particular very simple geometric constraint that might be interesting from an applied perspective and really helps you come up, you know, solve all of these problems that you have here with this, you know, invariance, that it's not invariant to rescaling and this monotonicity property here as well. So that's what I want to do, just add in a geometric. So I have this optimization problem. I'll go back to this original optimization problem here. So this is the optimization problem I want to study, and I'll add in a constraint, okay? So I'll add in a constraint, namely on K, on the, so here, this is an optimization problem over K. And I'll add in the following constraint, and, you know, it might seem kind of odd, but it's such a simple constraint. I'll just add in that all of the entries, well, off diagonal, since it's a positive definite matrix, have to be in the negative worthant. Okay, for all I not equal to j. Okay, so I'll just have my optimization problem. I'm optimizing a concave function over a positive definite cone. And I'm going to say as a constraint that, well, I'm not going to look at all positive definite matrices, but I'm only going to look at all positive definite matrices which off diagonally have all entries be smaller or equal to 0. Okay. Now that's quite a small set, in fact, it turns out. We can talk about how small it is, but of course doesn't have measure 0, right? It will have full measure. It will become smaller and smaller the more high dimensional you are. It's quite improbable, right? If you sample positive definite matrices that you'll ever find a matrix that has this structure. So I do need to motivate why I would put on a constraint like this, right? It's a nice geometric constraint, but it should also be interesting from an applied perspective. And in particular, I should also tell you why it is nice. And, you know, I am kind of motivating it here that you will be able to get rid of all of these problems that you had here. But just to give a bit of intuition into this here, from a statistical perspective, what this actually means. Well, we saw, right, I wrote out here what zeros mean. So this is what I define as K, right? K is the inverse covariance matrix. We saw what zeros means in the inverse covariance matrix, namely that you have this independent statement of these two nodes are independent given everyone else. Now, the question is, what does it mean if you have an entry be smaller or equal to 0? Okay, or what are actually the entries in the inverse covariance matrix? Now, and again, this would also be something that would be good for you to actually write down. If you write it down in the Gaussian distribution and you look at the entries in the inverse covariance matrix, they're actually the negative of the conditional correlations. So of the correlation of xi, xj given everyone else. Okay, so this entry here, so kij is the negative of this. Okay, this is super important. There is a minus sign in there. So if I'm putting on the constraint that all of these entries and these off-diagonal entries in K have to be smaller or equal to 0, that means I'm really putting on the constraint that all these correlations are larger or equal to 0. Okay, so this is a positive dependence constraint, not a negative dependence constraint. And so the question is, why positive dependence, right? Why would we care about positive dependence in applications? Why is this maybe a constraint that is meaningful, not just from a statistical perspective, because it will solve all these problems, but actually from an applied perspective, why would we care about something like this? So are there questions so far for this?
Sorry, could you say what you mean by correlation of xi, xj? Do you mean the correlation of the two variables? And then what does it mean that you're given these other variables?
Okay, so I'm looking at the conditional distribution. Okay, so I'll look at, you have a Gaussian here. I'll look at the conditional, first you write out what is the conditional distribution of two variables given everyone else. That's again a Gaussian distribution. And you can actually write out what the covariance matrix is and the inverse covariance matrix of that distribution. Okay, so I write out the distribution of xi, xj given everyone else. It's a conditional distribution. It's again a Gaussian. It has still mean 0. And it has some other covariance matrix, sigma. This is now a 2x2 matrix. And you can write that out, what it is. It's a 2x2 because now I only have two variables. And the correlation is just the 1-2 entry in this matrix.
Got it.
Or the covariance. Okay, and you can also take here the covariance. Does that make sense? So first go to the conditional distribution, then it's the correlation or the covariance in that conditional distribution.
Thank you.
Great. Okay, and so what we're saying when we're setting some of these entries to be equal to a smaller or equal to 0 means that these conditionals are actually these conditional covariances or partial correlations, if you normalize them, they're actually larger or equal to 0. Okay, so the dependence between xi and xj, even if you know all the other variables, it's actually going to be positive. And let me actually motivate it. I think it's important to motivate when you would expect. So it's a very strong positivity constraint. So it's a less strong positivity constraint to just say that the covariance matrix has all entries be larger or equal to 0. Okay, so actually your question, so it's great. So I have, and we'll see this afterwards. So I'm now saying something like, I could have the constraint that sigma ij is larger or equal to 0 for all I comma j. This would mean that the covariance, or let me just say that these are always normalized. I have ones on the diagonal. So all correlations are larger or equal to 0. Okay. That's one constraint, but I can have the other constraint that I just said, that kij is smaller or equal to 0 for all I not equal to j. here it doesn't matter. I can have for all ij, because on the diagonal, I'll also have larger or equal to 0. I can have this constraint, and as we just discussed, this means that the correlation between the nodes I and j, given everyone else, so even I'm assuming I'm fixing everything else, even then the correlation is larger or equal to 0. And this is actually just an algebra statement that you can show that if you have a positive definite matrix where all the entries are off-diagonal entries are smaller or equal to 0, it implies that all of the entries in its inverse are larger or equal to 0. Okay, so these statements here of covariance of xi, xj given everyone else being larger or equal to 0 is a stronger constraint than just the covariance of xi, xj being larger or equal to 0. Okay, and that you just get out of a linear algebra statement, right? I have a matrix, and you can prove it like that. I have a matrix where all off-diagonal elements are smaller or equal to 0. It implies that in its inverse, all entries are larger or equal to 0. Thinking about it from a statistical perspective, this constraint here is a much stronger positivity constraint than what you have on this side. I hope this provides a little bit more intuition. And so the question is, when would you expect something like this, right? When would you expect something where you have such really strong positivity constraints? What does it mean that I can condition on all the other variables? And so where you would expect things like this to happen is, if you look at just your stock markets, for example, you'll see that stocks, and this suggests that something like this positivity constraint is actually happening. But you see that these things usually move completely together, right? So, I mean, they don't move up and down the same amount, but usually when stocks move down, many stocks move down. And then when stocks move up, many stocks move up. But they might not move up and down the same amount, right? Like, for example, what you see here, well, some of them will move down or up a little bit more or a little bit less. But they show these very concordant behaviors of moving up and down. So even if you condition on all the other stocks, they will still be positive, like 2 of them will still be positively dependent. So this suggests that you have something like, this very strong positive dependence. And, I care about gene expression and gene regulation. So there also, you would have strong positive dependence if you have genes that, that they're sitting next to each other. And now a transcription factor, a protein comes in and turns these genes on at the same time because they're sitting next to each other. So they're all going to be turned on at the same time. So you'll see exactly this behavior, right? Just because genes are close in space, well, they'll be moving up and down together just because they're going to be turned on or turned off at the same time. So there are quite a few applications where you can kind of expect to see very strong positive behavior. And those are the kinds of applications that, we'll hope that we could maybe be able to model with these kinds of constraints. And I want to, in the last 15 minutes or so, just show you that what this constraint really means more generally, not just in the Gaussian setting. And then also to show you that this really works very well. Although it's such a simple geometric constraint, it actually works very, very well for these finance applications. Okay, so let me step a bit back. So in the Gaussian setting, you'll see that this is the constraint we're going to get to. Okay, it's just this geometric constraint. I want to define what this geometric constraint means a bit more broadly if you actually want to apply this to any distribution, not just the Gaussian distribution. And it will turn out that if you want to define it generally for any distribution, what this constraint is something that is known as multivariate totally positive of order 2. So it's a long word. So it stands for, I'll just use MTP2. And it's a really strange kind of condition. But just always think in the Gaussian setting, it will mean something very simple, namely all off-diagonal entries in the inverse covariance matrix are smaller or equal to 0. And it's really quite easy to show that, this definition that I have here implies that in the Gaussian setting. Okay, but what is this? And it's actually quite nice if you come somehow from more algebra. And if you know of total positivity, then this totally makes sense. So this is just a multivariate version of it. So you see in here something that is a 2 by 2 minor, right? And that's where this 2 here comes from, because it is, P of X. So you have 2 points, X and Y. and you're looking at the distribution, at the density or the distribution or the probability of seeing X and the probability of seeing Y. And then you look at the minimum of X and Y and the maximum of X and Y. So minimum of X, Y, and I have the maximum of X, Y. And you're saying that this product, the product of these two guys, has to be smaller or equal to the product of these two guys. Okay, so you see a nice 2 by 2 minor, if you know about total positivity of order 2, that's in the matrix, right? That all 2 by 2 minors are larger or equal to 0. So here, this is just a generalization, right, to distributions. And you know, these vectors here, X and Y, they can be higher dimensional, right? They can be in RD. So it is a multivariate generalization of total positivity. And, you know, it's kind of an interesting concept, right? And so the question is, why was something this crazy introduced? Like, why would anyone want to study something like MTP2? And this is just a bit of history. I mean, at that time, and still now, positive association is something, you know, that is quite important in statistical physics and statistical mechanics. And it's something that is, this is the definition of it. So a random vector is positively associated if and only if covariance, when you take any two non-decreasing functions, is larger or equal to 0. Now, the problem is that this is very difficult to check. I mean, you have to go over all non-decreasing functions. And so MTP2 was just introduced because, oh, I don't have it here. Oh, no, I do have it here. So MTP2 was just introduced because MTP2 implies positive association. Okay, so this here is very hard to check. But this here, well, this condition up here, this MTP2 condition is maybe a bit easier to check because you just have to check this for any points, any pairs of points in the sample space, and not for any non-decreasing functions, any pairs of non-decreasing functions. So that was really the motivation for introducing MTP2, not from a modeling perspective, just because it is stronger than positive association, which people really cared about at that time. And I should say that positive association in the Gaussian setting is exactly this. Okay, it means that all entries in the covariance matrix are larger or equal to 0. And MTP2 is exactly this, is that all entries in the inverse covariance matrix are smaller or equal to 0. And, you know, just this linear algebra statement will show you that one implies the other, but not the other way around. Okay, so this here is not true in general. So that's basically for the Gaussian setting, this FKG inequality here, which then turns out to be just a linear algebra statement. And let me not go through this, but let me just say here, this is exactly what I already said before. So MTP2 in the Gaussian setting is really just this constraint that all entries in the inverse covariance matrix are smaller or equal to 0. Okay, and this, you can really just write out the density function, and this will be quite immediate to see that MTP2 means this in the Gaussian setting. Okay, so this is the constraint I want to study. And you know, somehow I told you at the beginning, or when we talked about this constraint. So if you think about the positive definite cone and think of how often have you seen a matrix that is positive definite, where all entries in the inverse covariance matrix, or all entries in the matrix have all off-diagonal elements are smaller or equal to 0. Well, you've probably never seen such a matrix. It's like, it's really improbable for you to ever encounter such a matrix. I mean, this area, the volume of that space is just very, very small. In particular, it certainly needs to satisfy that all entries in the covariance matrix are larger or equal to 0. So if you look at stocks, well, you know, because of the thing of stocks moving up and down together, you usually have all entries be correlated. Okay, so even if you look at very, very large stock matrices, you'll see that the sample covariance matrix always looks like this, basically. So now the question is, what happens if I invert it, right? Is it really the case that all entries will become smaller or equal to 0? So this is a much weaker constraint, right? The next thing is a super restrictive constraint. But this is quite amazing, okay, that, you know, if you take small stock matrices and you invert them, then actually very often you'll get something that is indeed MTP2. Now, this is really quite surprising, I should say, because if you would just sample a correlation matrix, just uniformly at random, then the probability and here this probability here, we actually don't know it. This is really just from sampling it. We don't have a formula for the probability of, for how large the volume is of these MTP2 of these totally positive matrices. So we don't know it really, but if you just sample MTP2 distributions, you'll see that this shouldn't happen. This really shouldn't happen. It's with a very, very small probability that you ever find such matrix. So it's quite surprising that the first one that we ever tried, right? We certainly didn't go through 10 to the 6 different matrices. The first one we just looked at by just Googling, small stock covariance matrices is in fact MTP2. So it seems like this is quite a useful, or could be quite a useful tool for actually modeling when you expect things to be, very strongly positive dependent of each other. So this should motivate a bit of why we actually want to use this MTP2 constraint. And, we also have theorems that tell you that you should expect to see MTP2. I mean, that we can prove that this will actually be MTP2 if you, for example, have, where you should also expect it is something like phylogenetic trees. So any process that is on a tree where all of the branches are positive, you'll always get an MTP2 distribution, right? In phylogenetics, I mean, all of the species that you get out, they are strongly positively dependent because they have a shared ancestry. So that's what makes them be strongly positive dependent. So any of these processes on trees where all of the edge weights are positive, they will actually just become MTP2. And so, we think that probably these distributions, although they shouldn't appear just by random sampling, these distributions should really not appear that often. They actually appear quite often in data sets that we're looking at, just because many things are really kind of modeled quite well via trees and via processes on trees. But still, it's, I mean, this would be the motivation for actually looking at these, although it's a super restrictive constraint, it might actually be a useful constraint in applications. And this is just a very brief detour of saying, maybe some of you are now wondering, what about negative association? Well, so that's defined like this, but is there a version of, the opposite of MTP2, and will that also imply negative association? And that's unfortunately not the case. Okay, so the equivalent theorem for negative association does not hold. Sorry. And so there, it's quite nice. I mean, this book by P. Mantle is really quite nice on negative association. The right thing to look at there is strongly Rayleigh measures. I'm not going to go into it, but if you're interested in the same story for negative association, there's a really nice NeurIPS tutorial by Stephanie Jagelka and Subritsra on how to use negative dependence for all kinds of different applications. In particular, when you want to select things that are as different as possible from each other, right? So for example, here, when you're thinking of, if you've just bought the phone, then probably you're not going to buy a phone again in the next week, right? So Amazon should not suggest to you other phones if you just bought the phone. So it should suggest to you things that are orthogonal to it. And so that's for getting like variety or, different things, that's when you may want to use something that is negatively associated. So the kinds of applications we have here are very different to these applications here. But if you're interested in this, you can just Google this and you'll actually find it. It's a very, very nice tutorial. Okay, so I have like only 5 minutes or so left, 4 minutes left. So I told you that there are these problems for just the Gaussian setting, if you just do the standard graphical lasso, right, that you can, that you get something that is not invariant to rescaling, that you get something that is not monotone if you use graphical lasso. Also that, you already have this problem here that if you don't have enough samples, you don't even get a maximum likelihood estimator. That's why you have to use graphical lasso, because otherwise it's just not even well defined. And, let me not go through it too much, but let me just tell you that with that in fact under MTP2, so if you really add this constraint here of MTP2, of all entries on the inverse covariance matrix, be smaller or equal to 0, then all these problems are solved. Okay, so you get all these really nice properties. For example, this thing is not going to blow up to infinity, even if you just have 2 samples. So that's this first result here. So there was a proof by Slavsky and Hein in 2015. If you know about ultrametrics, so a really nice topic in linear algebra, then actually this proof is super fast. It's like 3 lines. So that's quite nice. And this here just says that, you know, all of these problems that we had there are kind of solved. That, you know, you do get consistency in the height. So you don't, as you see here, there is no parameter to tune, right? So there is no lambda to tune, and you just get consistency even in the high dimensional setting. And you even get something like monotonicity if you add an L1 penalty in addition to it. So those problems are kind of solved. So statistically, it's like really, really well behaved. So the question is just, you know, you get this kind of by adding a super strong constraint, right? So the question is, does this constraint actually work in applications? And, you know, this kind of suggests that, you know, hopefully it will, right? This kind of thing here, that actually already the matrix is MTP2 itself. And so I'll just end by actually applying it to a finance data set. And, you know, I mean, we didn't introduce MTP2 as a modeling tool for finance specifically, right? But it's quite interesting that, you know, it actually does. So if you just, so for finance applications for investing into stocks, one of the problems in the pipeline is that you have to estimate a covariance matrix among all stocks. So you can just estimate it under MTP2. Instead of, you know, all these other methods that people have developed, and some of them even just developed for finance applications. So really just with finance applications in mind. And you see here that although, you know, and in the paper, you'll have like 6 other methods. I just chose some of them here. So although these other methods actually have a tuning parameter, so they'll have 1 more degree of freedom, some of them were introduced just for finance applications. You actually beat most of them, in this case here, all of them, just by using MTP2. Okay, so it seems like it is really something that is, you know, that is inherent in many of these applications. And just this nice geometric constraint, it's a very strong geometric constraint. You know, it would be super interesting to know how large the volume is of these matrices, right? That are positive, definite, and all off-diagonal elements are smaller or equal to 0. Just know a little bit more about this geometric space. But, you know, this constraint is just, it works really, really well for finance applications. And with that, I will end since it's time. So I just have a little bit of an overview here. I think I already said everything. I think these MTP2 distributions not only have broad applications, but also lead to really beautiful theory. I only touched on very little of it, but you know, there is a whole lot of other stuff. Leads to nice semi-algebraic geometry, combinatorics, etc., etc. And I have the references here if you're interested. In particular here, I have all the total positivity references if you care about them. Good, thank you. I'm sorry for going.
Great, Caroline,
exactly to the
thank
hour.
you so much. Yeah. So I'm not sure if there's, I mean, we had a few questions during the talk, but I think it's a good time for questions also. So let me perhaps break the ice and ask, so are there other applications of this class of matrices or these MTP2 models in things that are not related to statistics? Somehow, why did people start looking at them?
Yeah,
or
so actually, so actually as a modeling tool, so Mike Jordan has started to look at them for, you know, for hypothesis testing, it actually helps you. It's a particular form of dependence between hypothesis tests, and then you can prove all kinds of results under MTP2. But that was also very recently that he started with this line of research, but before it was never used for modeling. It was really, the motivation was really just this, just to study, you know, positive association. So it was just introduced as a tool that implies positive association. Yeah, but now I think, yeah, it's kind of interesting that there will be more and more applications of, you know, it might actually be quite, it is quite intuitive because it's implied by trees, etc. And yeah, and maybe you can actually prove nice results like what Mike, for example, did.
Mm-hmm.
Yeah.
Great, thank you.
Any other questions?
I think Will has a question.
Caroline, you told us that MTP2 can be checked, right? Like on some with some samples. How do you check that? Do you just
perfect
look
question?
At this?
Yeah.
Determinant?
Yeah. No. So yeah. So you would actually have to go for all of your. So for all points in the sample space, you would have to go through this inequality. So that's one of the open problems of like, how do you actually from samples, how do you develop a hypothesis test for MTP2? Even in the Gaussian setting, how do you develop a hypothesis test for MTP2 is like super important because you get some data and then you want to know, is it actually an okay assumption? And then can I use it for modeling afterwards? And so that's one of the big open questions. Can you develop a powerful test for MTP2 from samples? Yeah, it's a great question.
Thanks.
Yeah. And yeah, it should be something, like your mind. Actually, let me also say another really big open question. If you come from some algebra background. So TPK is defined, right? That's all these K by K minors of a matrix have to be positive. MTPK is open. So there is no definition of MTPK. Okay, so it should be something nice, right? It should be something in a tensor and like some minors in a tensor, and it should be really, really nice. And there are like different things that MTP2. So what you need is something that it generalizes. So it should generalize whatever holds for TPK, right? It should also generalize whatever holds for MTP2. So there are different things that hold, for these distributions that are MTP2 that are known. So these two things, so you should find a definition so that, it really generalizes all of these nice things that hold for MTP2 distributions and that hold for TPK in a matrix. So this is open and, people have thought about, but I don't think that people have thought about it who are more from an algebraic perspective, who could actually come up with something reasonable in tensors, etc. Yeah. So I think there are many open questions here, like somehow at the intersection of, something algebraic, geometric, and probability theory.